So, gravity. Let's think about it. What is gravity? Why does gravity exist? How does gravity affect the motion of objects? These are really deep, fundamental questions that lead us to the nature of the entire universe. Why does an object fall? We know that it will fall, but it's actually not that well understood why it falls. What does really cause an object to go downwards? Like, what reaches out to push it down? How does it know that it should be moving? And how does it move downwards? Does it fall just like at a constant speed? Or does it fall at a constant acceleration? Or is nothing constant? Does mass affect the rate at which things fall? Do bigger things fall faster? And if they do they take less time to get to the bottom, more time? How does gravity work? These are the things I want to talk about today. So let's answer the question, does mass affect gravity? You can see here a GIF of me dropping two spheres. And we see these two spheres are entirely different masses. That this is a 5.1 gram sphere, while this larger one is over 100 times as large at 534 grams. So this is a very large steel ball. This is a very light wooden ball. Now we would expect if mass affected gravity, that this sphere, the solid metal one, would fall significantly faster. Like, not just a little faster. This is 100 times as massive. We should see that effect somewhere over here as the two fall. Now, I tried my best to release both at the same time. That is a very, very difficult thing to do because I am only human and my two hands cannot precisely fall at the same rate. So did we see them land at the exact same time right here? Well, no, we do not. We actually see the wooden ball hit just slightly before the steel one does. And now watch how they move together. Like the wooden ball stays just slightly ahead of the steel ball the entire time. The steel ball never closes in on that distance between the two. And so why would that, that's kind of counterintuitive, isn't it? Don't we expect this steel ball over here on this side to fall much faster? It's 100 times heavier. Why are we not seeing this in this image here? Well, that's because mass does not actually affect the rate at which things fall. This was first depicted or discovered by Galileo Galilei, one of the few scientists who we actually call by his first name, just Galileo. We really don't call him by Galilei, but most other scientists we call by their last names. I don't really know why. He was a man of the Enlightened Age. He lived during the Renaissance, and he did some of the most incredible scientific work of any modern scientist. He's often called the father of astronomy, the father of modern physics, and the father of the scientific method. He was a brilliant inventor and artist. His list of contributions to the scientific field is really so long and so in-depth. It's impossible to talk about all of them right now. But he was the first to study falling bodies and really gave birth to the field of kinematics. He really believed that physics principles could be expressed as mathematical laws. And so without his work, you would not be here studying physics the way that you are now. So you can thank Galileo Galilei for all of his good work in trying to understand the world through mathematics. And so he did a famous experiment by dropping objects off the Leaning Tower of Pisa, and these objects had different masses, and he timed the rate at which they fall, and he concluded that fall is independent, that the time it took to fall is independent of mass, that all objects just fall at the same rate, regardless of mass, which was very counterintuitive. I mean, it's counterintuitive even today. It doesn't feel like that should be true. And most people just assumed that heavier objects will fall quicker. But we find with really accurate measurements, especially today, that they do not. Well, you might be asking, I ask you, can you think of anything that counteracts this? Is there something you can think of falling that definitely takes more time? A lighter object that takes a lot longer to fall than a heavy object? The answer should be yes, because we've all seen things with high air resistance fall before. You drop a piece of paper and a rock, What's going to take longer? Well, the piece of paper floats and flutters all the way down because in this case, air resistance has a big effect on the motion of falling objects. And so anything with a low mass and a high surface area, like a piece of paper, we cannot just ignore the effects of air resistance. This was also tested on the moon. In 1971, astronaut David Scott dropped a hammer and feather on the surface of the moon. And we can see it's a very grainy image because it was 1971. But this hammer and this feather do reach the surface of the moon at the same time. Also notice that they fall very slowly. Would you expect this? Yes, the moon is much smaller in comparison to the Earth. And so what affects the rate at which things fall? Well, the planetary body that you are on. And so think about this. Do falling objects accelerate? That was another question I asked initially. Do they accelerate or do they fall at a constant speed? We know that mass does not affect it now, but do they accelerate? Well, if we have a ball, such as this kangaroo over here, and this ball, you are just holding it in your hand, it's initially at rest. Well, when you let go, it will move from a state of rest, not moving, to a state of motion. Well, then that means that the velocity has changed. You have some kind of non-zero delta V. And that took time for that velocity to change. Nothing happens instantaneously. All things take at least some amount of time to happen. So this ball goes from not moving to moving. So that means the ball must have accelerated. So anything that falls must accelerate. And we can ask ourselves, okay, just because it accelerates a little bit from some v to from 0 to some not 0 final velocity, does that mean it keeps accelerating or does it stop accelerating somewhere? Well, ask yourself this. Is there a difference between falling 4 feet, 40 feet, and 400 feet? Absolutely. You continue to accelerate through their falls. We know this now. And so we know that it is a constant acceleration. And so we have the exact value at which objects accelerate. We call this value the acceleration due to gravity. It's also known as little g because we always approximate it with this little g sign. Never big G, always little g. And we will see that why probably in a month or two when we talk about big G. But for now, let's just keep it easy with little g. It is always equal to 9.8 meters per second squared on the surface of Earth, but it is going to be different on different planets or planetary bodies. On the moon, our acceleration due to gravity is about 1.2 meters per second squared. On Mars, it's about 3.4. On Jupiter, I think it's about like 17 meters per second squared. So different size objects produce different planetary objects produce different gravity. But for now, let's just keep it nice and easy with 9.8 meters per second. Free fall is a term that describes an object that's being accelerated by gravity and only gravity. And weirdly, we do not have to be falling to be in free fall. Think of throwing a ball upwards. As soon as that ball leaves your hand, what's the only thing affecting the motion of the ball? We're assuming there's no wind like coming in and blowing it or anything. As soon as that ball leaves your hand, it's starting to slow down because of gravity. This whole time, there is gravity acting downwards on that ball, and eventually it's going to reach its peak, and it's going to not have any speed anymore. Gravity will still be there the entire time, but things do not have to just be going downwards to be in free fall. As soon as anything is being accelerated due to gravity, it is in free fall. And that could include objects going up or objects that are thrown forwards are also in a state of free fall. We'll talk about that in our next unit. But for right now, free fall, anything that is only being affected by gravity is in free fall. Okay, now let's talk about some free fall symmetry. Let's really analyze what's going on if you hold out a ball in your hand and you throw it up and it comes back down. So step by step. Initially, you give that ball some upwards velocity. You accelerate it upwards, and gravity is always acting downwards. Notice at every single stage in here, there is always gravity. You can never turn gravity off. It is constantly and never changing, pulling something down. All objects. Everything on this planet is always has a G value pointed downwards. Sometimes that doesn't mean you're always falling downwards. So if you're on the ground, you still have weight downwards, but you're not falling downwards because the ground is keeping you right back up. And you have a zero acceleration because they cancel out. And we'll talk about forces in our next unit. But at every stage in this, this ball has gravity acting downwards. Now, when we throw it upwards, we give it an acceleration upwards, our hand pushes it up, and then we make it have a non-zero velocity in moving upwards. We move from T0 to T1, now our ball is moving upwards, but as soon as it leaves our hand, we only are applying acceleration when it's touching our hand. As soon as it's out of our hand, it begins to slow down. It's moving upwards, but it begins to slow down until we get to here. This is when it's at its maximum peak. It stops for the briefest moment because it's slow, it's going up, it's going up, it's going up, it stops, and then it comes back down. And then, so this is when the ball briefly stops and then starts to fall again. From its peak, it then begins to fall, speeding up and speeding up and speeding up, and reaches its maximum downward velocity right before it reaches your hand again, and then you catch it in your hand, and your hand prevents it from going any further. Your hand accelerates it upwards, slowing it down from its initial position. Think about what this would look like as a velocity time graph. The ball is initially not moving. It's thrown upwards by your hand, so this black part is your hand accelerating it. And then it is in free fall the entire time. And notice the slope here is constant. And what if you were to guess what this slope would be equal to? I bet you could guess it. Negative 9.8 meters per second squared, because that's the acceleration due to gravity. And notice it doesn't change even when we get to T2 and it stops. The acceleration due to gravity is still a constant. And now we're accelerating it downwards, making it go faster and faster. And then we get to right before it hits our hand, and then our hand stops it and we bring it back to rest. So that's like an in-depth analysis of something moving upwards and coming back downwards. And we can see all of these values labeled. Notice that the blue and the green are both acceleration vectors, while the red is a velocity vector. We talked about, too, anytime velocity and acceleration are in the opposite directions, that means slowing down. Anytime they are in the same direction, that means speeding up. Slow down, speed up. All right. Let's move forward. So hopefully you might have noticed two different things about this. When something is thrown upwards, there's a thing we call free fall symmetry. And the amount of time it takes to go up is the exact same amount of time it takes to go down. This would be represented here by, I'm going to clear this, maybe do a nice green. The time it takes from here to here, time, is equal to the time it takes to move from here to here. Always and forever, the time it takes to slow an object to rest, move upwards, is going to be the exact same time it takes to move that object down from rest to the same speed. And to the same speed is also the other bit of free fall symmetry. This speed right here and this speed right here, they are the exact same. This V is equal to this V. We'll say V initial is equal to V final, but in the opposite direction. So whatever velocity you throw this ball up with, it's going to have to come down at the same speed. I think that makes perfect sense if the times are the same, that you had so much time, you were given, I don't know, let's say 2 seconds to move up. Well, then you're only going to have 2 seconds to move down, so T is the same, so T1 equals T2. The acceleration is the same in both cases, A1 equals A2, which is just equal to G, because that's no different. And if those two things are the same, well, of course, your change in velocity is also going to have to be the same. We can approximate that with the acceleration formula. Delta V equals A times T. So this is free fall symmetry. Everything, whatever it takes, however long it takes to go up, it takes the same amount of time to come down. And then the final velocity of the object when it returns to the initial position will be equal but opposite to the initial velocity. So we can really just summarize that T1 equals, we'll say T up equals T down, and V up equals V down. That's some symmetry of free fall. Let's do an example of this. An object is initially thrown upwards at a speed of 29.4 meters per second. How long will it take the object to reach its maximum height? So we initially, VI is thrown upwards at 29.4. It is going to be moving upwards, 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 until it reaches its maximum height, which of course we know, at its maximum height, the velocity must be 0. And another color I'm also going to add in here, that I know what the acceleration is. I'll call it negative 9.8. Notice positives and negatives with this 9.8. You might have a question about this. Should this always be a negative value? Totally depends on how you want to set up your motion. As always, we can set up our coordinate system to be whatever I want it to be. I am inherently saying that where we start is my 0, x equals 0. And then I'm going to say that my upwards direction is positive, making my downwards direction negative. I could flip-flop that if I wanted to. I could set it that this is equal to 0, and I start negative some position downwards. It's totally up to you how you want to define it. Just define things to make sense. And often it makes sense to just make going up positive and going down negative. So we're going to do just that. I know my initial velocity, I know my final velocity, and I know my time, I know the acceleration due to gravity. Can I figure out how long it will take the object to reach its maximum height? Well, I don't really know a whole lot of acceleration equations, but I do know acceleration is equal to delta V over t. In this case, I know my acceleration is equal to negative 9.8. It's due to gravity. I know my change in velocity is going to be negative 29.4. And I'm wondering how long is it going to take the object to slow down at this rate. T is then, if I just rearrange this equation, it's going to be negative 29.4 over negative 9.8. And I get that the time it takes is equal to exactly 3 seconds. And I got that by doing negative 29.4 divided by negative 9.8. Again, I'm just plugging the values that I have. I always know A when it's a gravity problem. I know how the velocity is going to change. And so I get a time of 3 seconds. How long will it take the object to return to its initial position? What I'm saying here is that it takes 3 seconds. T up is equal to 3 seconds. Well, do I know what T down is? Absolutely. From free fall symmetry, I know that's also going to be 3 seconds. You could also recalculate this and figure out how long is it going to take to accelerate from 0 to negative 29.4. Given that it falls at a rate of 9.8, and we end up doing the exact same calculation, and we get 3 seconds again. So how long will it take the object to return to its initial position? 6 seconds total. 3 to go up, 3 to go down, 6 seconds. And what will be the final speed of the object? Again, free fall symmetry tells me that if I go up at negative 29.4, I will go down at, I'm sorry, this was initially positive. If I go up at positive 29.4, I'm going to go down at negative 29.4. So VF is going to be the same value but opposite direction of negative 29.4 meters per second. Sketch a VT graph of this motion. Easy. We start on this velocity time graph at 29.4. We end at negative 29.4. We have one constant acceleration, so I should have one constant slope. At 0, 0, at time equals 0, I'm moving upwards at 29.4. At time equals 6, I'm moving downwards at 29.4. And all I got to do is connect the dots, and I should be at rest in the middle. And that's what our velocity time graph looks like. The slope of this velocity time graph is going to be equal to negative 9.8. And that makes perfect sense that it would. Perfect sense that it would. Here we are at rest right at this. This corresponds to the point when we're moving upwards, and then we come to a brief instant of stop, and then we start to accelerate downwards. And that's how all free fall, anything moving up and coming down, is really going to look just like this. All right, if I wanted to make a position time graph of this information, could I do that? Absolutely, it would look exactly like this. The whole thing took 6 seconds. Here, notice I do not have a constant slope. And does that make sense? Actually, it does. The slope of a position time graph, remember, tells me about the velocity. And here, we see that the slope is changing at every single case on here. It is first becoming, it starts very positive, and then it's slowly becoming more and more horizontal until we reach to here where the slope is perfectly horizontal. And then it's slowly getting more and more negative, getting faster and faster, faster in the opposite direction. And we see free fall symmetry everywhere here, that we start going up at 29.4. The slope coming down is the exact same. These are also opposite slopes from each other, both 19.6 and then 9.8. And we see that the whole thing going up takes 3 seconds, and the whole thing coming down takes 3 seconds. Free fall symmetry will look exactly like this. All right, dropping objects. We are almost done, guys. Turns out that there's an easy way to figure out how long it'll take an object to fall from a known height. All you got to do is plug it into this formula. H is the height in meters. Make sure it is in meters. And G is the acceleration due to gravity. 9.8 meters per second squared. I don't know why I lost my square there on Earth. So we can easily plug it into that formula and figure that out. We can try that right here. How long would it take a 10 kilogram object to fall off a 100 meter cliff? Well, T fall tells me I would do the square root of 2 times 100 for my height divided by 9.8. Well, you might be asking, Mr. Williams, what about the 10? Where do we put the 10? Well, we know, guys, does it matter how heavy an object it is? Is that going to make it fall any faster or slower? No, this does not matter. And get used to me giving you random variables in hopes to confuse you, because that's one of my favorite things to do. And you need to know this 10, you don't need it. You don't need this at all. What we need is that this is the height. And we know that it's 9.8 because we're always going to assume we are on Earth unless otherwise stated. So we get that we can figure out exactly what this is. We throw this into a calculator and we get the time to be 4.5 seconds. That's how long it's going to take to fall 100 meters, 4.5 seconds. We dropped a rock off a bridge and recorded the time it took to reach the ground. If it took 8 seconds, how high above the ground is the bridge? Can I use the same equation? Sure, why not? The equation is T fall equals square root of 2h over g. I know in this case what g is. I know what T fall is, it's 8 seconds. I know what 2 is, it's 2. Can I plug in and solve for h? Absolutely, it just takes a little bit of algebra. We now start 8 is equal to the square root of 2h over 9.8. I know 8, 2, and 9.8. I do not know what h is, so I just need to get there. Step 1, square both sides. Now I have 64 equals 2h over 9.8. Next step, on getting h by itself, is multiply both sides by 9.8. We do 64 times 9.8, and we get 627.2 is equal to 2h. I don't want to know what 2h is equal to. I want to know what h is equal to, and I get that h is equal to 313.6 meters. Also, this would check out, right? If it only took 4 seconds to fall, 100 meters took us 4.5 seconds. We would expect a number higher than 100 meters. And we got that. 313 meters is how far you would fall for 8 seconds.